Hello, everybody. This lesson is about binary to decimal conversions and decimal to binary conversions. The goal is that at the end of this lesson and with homework and everything else, you should be able to convert back and forth between binary and decimal with an accuracy rate of 70% or better. Uh, now, I'll put that out there, but really honestly, I expect you all to be able to do much better than that. Let me reassure you, it's not particularly difficult if you take your time and pay attention to what we've got going on here. So what we're going to do in a moment is we're going to go ahead and I'm going to show a couple examples of converting binary to decimal so that we go from something that you're absolutely not familiar with to something you are more familiar with. And so that'll kind of set the stage, get you a little bit more comfortable, and then and I'll show you a methodology for doing that. Again, pretty simple stuff, and we've got it all laid out for you. Now, after that, then we're going to go decimal to binary. You know what? It's not hardly any more complex than it is, but even better, there's going to be two methodologies to do that, so you can pick which one you like. So without further ado, let's go over there and take a look and see what that looks like. So first of all, a quick tour of the place that we will be working. You will not have this on your test. I put this up here because, as you will find shortly, I am not particularly comfortable with the stylus. My handwriting on a pad, my handwriting is awful. And this stuff doesn't lend itself to typing particularly well, at least not, not as people watch. I hate watching people type. I'm not really fond of watching them writing by hand, but I can do that quicker, particularly given you have to do things with superscripts and all that kind of stuff. So a lot easier to, so I kind of set this up to make it easy for you guys to kind of follow what's going on. Also, I wanted you to see there's an opportunity here for you to see some patterns and how stuff go that in reality should make things easier for you as well. So let's go ahead and get started. So the first thing we're going to do, as I promised, is we're going to go ahead and we're going to convert a binary number to decimal. And we'll start with a small one first. Not that it's going to make any difference to the process, but it'll go a little bit quicker if we do it that way. So let's just say we saw 1011. What is that equal to? Well, first of all, let's think back to when we were first learning about numbers. Remember that places have distinct values. When I say places, I mean from from the least significant digit to the most significant digit. The correct mathematical terminology for that, but that first column of numbers has a value based on where it is placed. So the first column in decimal, which is what we all learned in school, was what we called the ones column, or it was really what you see here. It was 10 to the 0 power. This is called the identity there's an identity property or unity property, depending on different branches of mathematics out there, that says any number raised to the power of 0 is equal to 1. So 10 to the 0 or 2 to the 0 is both equal to 1. What does that mean? It means that the numeral that you see in that column times the value of the place is the number that's being represented. So what does that mean? That's a lot of big words there. So we know that 10 to 0 we called the ones column. I think you probably did too when you went through school. The second column over, 2 to the 1th power, is the tens column. I'm sorry, not 2 to the 1, but the 10 to the 1 column when we were going through school was called the tens column. The 10 to the 2nd column was the hundreds column, thousands column, 10,000th column, 100,000, million, and 10 million. That would be the equivalent if I were to write this out here. So just, we got a 10 to the 1, we got a 10 to the, I'm sorry, 10 to the 0, 10 to the 1, on and on, 10 to the 2. That was ones, tens, hundreds, thousands. All right. All right, we have the exact same. So that idea carries through into binary as well. In binary, 2 to the 0 is just like 10 to the 0. That's 1. However, in binary, you're only going to have 2 digits, 0 or 1. So it's either going to be that value or it is not going to be that value. Right? So 2 to the 1 is the 2's column, and 2 to the second power is going to be the 4's column, and 8 and 16 and all that. So let's do that conversion. It's pretty straightforward. So you see this decimal value here. So think about, so I've done probably the hardest part of the work for you, in that you got to remember what the place value is worth. And because I have it written down here, it's pretty straightforward. However, it's straightforward even if I've not written it down. Look at the pattern. We start with 1, times 2 is 2, times 2 is 4, times 2 is 8, times 2 is 16, 32, 64, 128, on into infinity. 128, 256, 512, 10, 24, 20, 48, 40, 96. It's that simple. If you've done it, if you've done it any length of time whatsoever, these things become pretty straightforward stuff. So once you understand the place value, then in binary it's very simple. You don't have to do any figuring. Like, for instance, in decimal, if you're in the tens column, if you've got a 7 there, you still have to do a multiplication to get the value. You got to do 7 times 10. If you were in the hundreds column, there was a 7 there, you'd have to do 7 times 100. But in binary, it's on or off, right? I mean, we all know that, right? So that means that if there's a 1 here, if there's a 1 in the ones column, the value is 1. If there's a 0 in the ones column, the value is 0. If you've got a 1 in the twos column, it's 2. And if it's a 0, it's 0. So it's always going to be 0 or that number. So it's going to be from the right hand, 0 times 0. Your options are in the first column, 0 or 1. And the value is going to be 0 or 1. That's it. In the second column, it's going to be 0 or 2. There is no 1 value in the second column. It is because it's powers of 2, right? Same thing here. It's 0 or 4, 0 or 8, 0 or 16. So 1 simply represents the value of that place. And a 0 indicates that there's nothing there. So in many ways, it's actually simpler than decimal. It's just different. So let's go down and do this. So we got go from the right to the left. We got 1 in the 2 sub 0 or 2 raised to the power of 0 column, or the 2's column, if you were, or the 1's column, I should say. So that number's 1, and we see that in the 2 raised to the power of 1, or the 2's column, there's a 1, so that's 2. There's nothing in the 2 raised to the power of 2 column, so that's a 0. And there's a 1 in the 2 raised to the power of 3 column, and since there's a 1 there, that's 8. So 8 plus 2 plus 1 is 11. Okay, that's how you express 11 in binary. Let's do another short example, and then we'll do a couple long ones, and then we're going to move on to something else. And So again, starting from, there's a 1 in there, so we're going to do 1 plus 4 plus 8, 12, 13. It's that simple. Okay. That's a short example. Let's do a longer one. 1, 0, 0, 0, 1, 1, 0, 0. And so that becomes 128 plus 8 plus 4. And that's 16 plus 4 is 20. Put down the 0, carry the 2. And 2 plus 2 is 4. That's 140. Okay. There's no magic here. There's, nothing in the hat. It is a pretty straightforward process. Once you practice it a few times, you'll find that it's just really not that much to worry about. We're going to do one more big one, and we will do 1, 1, 1, 0, 0, 0, 0, 1, and that gives us 128, 64, and 32, and 1. So let's add those up. 128, 64, 32, 1. 8 plus 4 is 12, plus 2 is 14, plus 1 is 15. Carry the 1. 1 plus 2 is 3, plus 6 is 9, plus 3 is 12. Put down the 2, carry the 1. 1 plus 1 is equal to 2. So this is equal to 225. Okay? All right. That is binary to decimal conversion. There's really not much more to it. You've seen both a couple of short examples. You've seen a couple long examples. Now let's do it the other way. Let's go decimal to binary. Now, there are two methods. Both of them are equally easy to do and equally easy to understand. I'm going to lead off with the one I use most often because I use it most often. Again, there's no reason for it. This is the one I use more often but let me go ahead and do that. I jokingly call this the Gazinta method. And that's because it goes back to the days, because this is largely driven by subtraction. And I think back to the days when we were doing this with our teacher, and the teacher would go, okay, does this number go into that number? And then as time went by, we would just it would got contracted to Gazinta. All right. So let's take 220 as our decimal number. So we'll start with 220. And the first question we ask is, does 128 here, start at the left-hand side, go into 220? Yes, it does. So we'll put a mark down here. Oops. Not sure why that happened. But, because I hit the switch. That's right. So we subtract 128 from 220. So this becomes 2, and that becomes 11, which gives us 9, and that's it. 92 is the answer there. Next question. 64 will go into 92. Yes, it does. So 12 minus 4, 8. 8 minus 6 is 2. Okay. Does 32 go into 28? The answer is no. So we put a 0 here instead of a 1. So does 16 go into 28? Yes. The answer, so we subtract 16 from 28, and that leaves us 12. Next one, 8 go into 12? Yes, it does. Leaves us 4. Does 4 go into 4? Yes, it does. And we're done. Nothing else to do. As you would do in decimal, you have to fill in the least significant digits with zeros just as placeholders so that we know the proper value of this first one. And that's all there is to it. Let's go back and double check our work. 128, 64, 16, 8, and 4. 8 plus 4 is 12, plus 6 is 18, plus 8 is 26, plus 4 is 30. Carry the 3. 3 plus 2 is 5, plus 6 is 11, plus 1 is 12. Put down the 2, carry the 1. 1 plus 1 is 2, 220. So we get the right answer backwards and forwards. Now again, let me caution you here. You saw me double check here, and there's a good reason for that. It is a simple process, and sometimes simplicity can be misleading. It is simple, but it is also exact. And that's the big thing about mathematics, right? It is exact. You know, you can, if you gave me 219 or 221, that would still be the wrong answer. It's not close enough here. It needs to be 220. So, take your time. It's one thing for me to fly through this. I've been doing this for a very long time. Probably twice as long as most of you have been born. But, you know, don't be misled by that ease. You need to take your time and you need to double check so that you get recognition for what you know. So, that's method 1. We've seen that now in a couple examples. Let's talk about method 2. Method 2. Okay? We'll start with 220 again. Method 2 is a division method. So what we're going to do is we're going to keep dividing by 2 until we get to a 0 result. So let's start here. 2 goes into 120, 110 times with a remainder of 0. Now it's going to be very important that you keep track of the remainders because the remainders are what are giving you your answer. So we take 110 and divide it by 2. And that turns out to be 55 with a remainder of 0. And we take 55 and we divide it by 2, and it turns out that that is 27 with a remainder of 1. Okay, one thing I want to point out here, since we're at this point, you may not be familiar with this remainder notion, this remainder notation rather, and that's all right. You may not have been exposed to it. My youngest daughter is an elementary school teacher, and she tells me that they don't teach fractional division any longer, what I'm calling fractional division. In other words, they don't do a form of division any longer that preserves the remainder. Because again, if we look at this, if we were to do this in decimal arithmetic, when we divided 55 by 2, the answer would have been 27.5. Okay? And that's the same answer. But it's expressed differently. And here's the challenge. Why do we insist on having you guys understand and use the remainder? And that is because as computer science developed, we found that that ability, that finding that integer remainder was quite useful for doing some types of work. So I would come up with things like encryption, for instance, or random number generators, or those kinds of things. We often really prefer to understand the remainder more than we actually care about what the actual other number is. We cared more about the remainder than the whole part. And so it has real utility in computer science. Another way to think about it is that we often frequently in computers are modeling what happens in the real world. And in the real world, sometimes the fractional component doesn't make any sense. And for that, I would go back to when I was a young lad. Oftentimes, a statistic that you would see frequently would be of the effect that the average American family has 2.5 children. Well, what does a 0.5 child look like? I know what 2 children look like, but I don't know what 0.5 children look like, and I'm not sure I'd want to know. But, okay, that's fine. I get it. We all know that really was just a result of the averaging methodology, that it really meant that some people had 2, some people had 3, some people had 0, some people had 5. And all in, when you looked at that over the number of people that you actually looked at and the number of families that you looked at, you did the math and you came out with a number called 2.5. Okay, we all understand that, and it's not that big a deal, but sometimes it is important to understand, you can't have a fractional person. And this is going to play heavily into your programming coming up, and it's an area where I saw a lot of people have trouble with. So I'm going to have another short video on fractional division so that you get an idea how this is derived. You've seen me do it, but you haven't seen me, so we'll spend a little bit more time on it so that you can be fully comfortable when we get to there. Another example of why we care about remainders and why we care about doing this kind of more of an, I guess the right term rather than calling it fractional division is integer division. The reason that we care about integer division, another reason that we care about integer division was more than 20 years ago, when I first started my master's there at Midwestern State. I took a class called computer graphics. I thought it would be fun because I was, in those days, it was the early days of graphics and computers, and the idea of being able to do graphical kinds of things with colors and lines and all that good stuff, and arcs and all sorts of good stuff I thought would be really quite fun. And it was extremely interesting and a very valuable class. However, it was not fun. It was a lot of work, and I barely scraped by in there. Why? Because it was all about the math, and the big thing was that computer graphics, at least in those days, was an awful lot about developing algorithms that helped us to avoid decimal math and stay in integer math. Why would we want to do that? The biggest reason was because decimal math costs more in CPU time than integer math. And given the numbers of computations that needed to be made, that added up. And so we were looking for the efficiencies of doing integer math because of the sheer number of calculations that needed to be made. Now, I don't know if that has changed a lot with the advent of dedicated graphic processing units and stuff like that. I really haven't paid close attention to that. My mind's been elsewhere over the last, X number of decades. But the important thing is, yes, this integer division and the remainder is still very critical within computers, so it's something you need to be familiar with. All right, so that public service announcement complete, let's continue with our example. 27 divided by 2 is 13 with a remainder of 1. And I should have started this before, so let's go back and get caught up. This first one was a 0, reading up from the bottom. Second is a 0. Third one is a 1. And the fourth one is a 1. Again, tracking the remainder. 2. 2 go into 13. 6 times of the remainder of 1. So we put a 1 there. 2 go into, let's move over here because I'm running out of room. 6 for remainder 1. 6 divided by 2 is 3 with a remainder of 0. So we put a 0 there. And 3 divided by 2 is 1 with a remainder of 1. Put a 1 there. And we're still not at 0. You keep doing this until this is 0. This number here, this first number 1. So we go 2 goes into 1. Goes into 1 0 times with a remainder of 1. Now we're done. So this last one goes out there. So double check our work as you've seen me do before. 128, 64, 16, 8, 4, and that's it. 8 plus 4 is 12, plus 6 is 18, plus 8 is 26, plus 4 is 30. Carry the 3. 3 plus 2 is 5, plus 6 is 11, plus 1 is 12. Put down the 2, carry the 1. 1 plus 1 is 2. 220. So it checks out. All right, let's do one more, and then we will call this a good. Oops, thought I had that. There we go. And all right, okay. Let's do 173. 173 divided by 2 is equal to 86 with a remainder of 1. So I'll put that 1 up here. 86 divided by 2 is going to be 43 with a remainder of 0. We'll put that 0 there. 43 divided by 2 is equal to 21 with a remainder of 1. That 1 there. 21 divided by 2 is equal to 10 with a remainder of 1. 10 divided by 2 is 5 with a remainder of 0. 5 divided by 2 is equal to 2 with a remainder of 1. That 1 there. And then 2 divided by 2 is equal to 1 with a remainder of 0. And 1 divided by 2 is equal to 0 with a remainder of 1. Okay, that should be our answer. Let's double check. 128, 32, 8, 4, and 1. 8 and 2 is 10, plus 8 is 6. 8 and 2 is 10, plus 8 is 18, plus 4 is 22, plus 1 is 23. Down to the 3, carry the 2. 2 plus 2 is 4, plus 3 is 7. Carry down the 1, 173. That's where we started. We look, all right, and so our answer is correct. So we've successfully done that. that's all there is to it. Now, what we covered in this thing was binary. In this particular lesson, we covered binary versus decimal. We saw how the place values were determined the actual numeric values. We in both decimal and binary, we compared and contrasted. We did that to help you compare with something you're familiar with. So we compared and contrasted between those two, and then we showed you binary to decimal conversion, so you could see how you convert from the unfamiliar to the familiar. And then we did two different ways of converting from decimal to binary. Both again are equally useful and equally simple. The objective of this lesson was for you to gain the skills and competency necessary to be able to convert between binary to decimal and decimal to binary with at least a 70% accuracy. And hopefully with these examples and handouts, the homework, you're going to be able to achieve that kind of score on your quizzes and exams. So appreciate your attention, and we'll look forward to seeing you in our next lesson.